So the idea is going to be solving differential equations by power series. They are going to give you the instruction, okay, if they want you to do this method. So what is going to be solving differential equations by power series? There's no integration. It's all algebra. It takes times. So what I'm going to do, briefly, we need a little bit of the power series from calculus 2. So I'm going to discuss how much, or whatever we need. Okay, so you don't need anything else other than the one that I'm going to discuss. Okay, so usual definition of the power series. So I just remind you, recall that if you have a sequence of numbers, C0, C1, C2, Cn, etc., going to be numbers or a sequence of numbers are numbers. Okay, are numbers. Then this expression sigma of Cn x to the n from 0 to infinity, which is going to be C0 plus C1x plus C2x squared. Just continue forever. You know that this is going to be a power series of x is power series of x or of powers of x. Powers of x. There's some other expression that we're going to talk about later. Okay, that's it. You know that in this power series, if you replace x by any number, that gives you a numerical series. That series can be convergent or can be divergent. So there is going to be a domain for x that this procedure would happen. That domain is going to be called domain of the convergence, and we usually write it down as an interval. And that interval would have a kind of a length. That length is going to be called the radius of convergence. Okay, so I'm going to remind you those two. So this is going to be the case. So if you have positive numbers, okay, so if the radius, the radius of convergence, convergence is going to be r, then you know that this means this series is going to be convergent for different values of x. And so if you drop one x over here, you get the convergent series. So we get a set of numbers. Those set of numbers introduce a function. Okay, then the function. Okay, then we are going to have a function. Function would be f of x. That would be defined by this power series. Cn x to the n from 0 to infinity. Okay, this function can be defined now. Can be defined, and the domain of the function is going to be the domain of the conversion of the set. It's going to be defined when the absolute value of x is going to be less than r. So there's going to be an interval, negative r, positive r. If you take any number in that interval, you get the power series. Okay, so it's a kind of this is the variable x. Okay, you drop it into the function machine, but this machine would give you the power series. Okay, so it's going to be f of x equal to the sigma of Cn x to the n from 0 to infinity. Okay, this function, we say that this function is defined by a power series. Okay, so f is going to be called, f is called a function. It's going to be called a function defined by a power series or a power series function. Like a power series. You know that this power series, if you want to check the convergence of this series, you're going to have a sequence of a partial sum, and you put them together, you get this one. There are some famous ones that we are interested in. Okay, so we're going to use the following. For example, you have to know this for this section, okay? So you can add it to your section of the formulas that you have. Okay, for example, we need exponential function, of course. E to the x is 1 plus x plus x squared over 2 factorial and plus x3 over 3 factorial, and you continue. The power series for the exponential function in condensed form is going to be e to the x is equal to the sigma of x to the n over n factorial, n from 0 to infinity. The domain of convergence of this series is all real numbers. That's why we like this one, because the domain of the e to the x is all real numbers. So this is true for all real values of x, for all values of x. You should be familiar when we see this one. You should be familiar and know that, you know that this is e to the x. You can replace x by any number you like. So if you want to find e to the x squared, so you replace the x by x squared. If you want to find e to the 5x, you do the same thing, okay? So be ready for it because this x is free. So this is very popular when we do the power series solution of the differential equation. This is the first one that we need. The other one that we need is the sine and cosine. Okay, so for the sine function, you know that sine is going to be the odd power of the sine. The power series of the sine will be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. So in condensed form, the sine x is going to be equal to the sigma. Okay, it's going to be sigma, and this is going to be a negative 1 to the n, x to the odd power, which is a 2n plus 1 divided by the 2n plus 1 over factorial. Okay, but n going from 0 to infinity. So if you get this odd power, that would represent the sine. Yeah, of course, the sine x is defined everywhere. So this series is defined everywhere, okay? So it's going to be for all. Again, the radius of convergence or the domain of the convergence is going to be all real numbers. So this is going to be true for all values of x. Okay, so this is going to be power series for the sine. Any question? You can differentiate it to get the cosine. If you differentiate the sine, that gives you cosine x. You see, if you differentiate this one, each one of them 1 by 1, so that gives you 1. Okay, on the top, you see that gives you 3x squared. You can simplify one of the 3 over here, so that make it into the x squared over 2 factorial. You can do the same thing to the other. Okay, that gives you the next one. It's going to be even power. It's going to be x to the 4th over 4 factorial, etc. Okay, so in condensed form, you get the cosine of x is going to be equal to the sigma of negative 1 to the n to the top. Okay, x to the 2n. Okay, x to the 2n divided by 2n factorial. 2n factorial, n from 0 to infinity. Again, cosine is defined everywhere, so this is going to be true all the time for all x. For all x means you can change x into the x squared, 2x, 5x, and bring the new series, okay? So they are the most popular one. Examples that I'm going to give you are going to be around in these 3. If it's going to be anything else, you can just write the series. But if it's going to be familiar, you may change it into this format. Okay, any question? Now, you know that there is another way that you can find the. So this is the case that the power series is given to you. If it's going to be convergent, so you can introduce a function. So you know that there's going to be another way. If a function is given to you arbitrarily, and the function is going to be differentiable, you can find a power series for that function yourself. In order to find it, you can use the Taylor theorem. Remember Taylor series or the Maclaurin series. Okay, so I give you that one too. So we usually go with the Maclaurin. So this is going to be the case. And because I'm not going to use the Taylor format, but this is an option, and I give you one example on this one. So that's why I need it. So in general, if you like, in general, if a nice function is given to you, have a function that's going to be differentiable all the time, that function can be estimated. Or f of x is going to be like of the time is equal to, but not in general. Okay, I'm going to introduce the Maclaurin series or Taylor series at 0. And this is it that give you f of 0. Okay, f of 0, then we get, it's going to be f of 0, then we get f prime of 0. Okay, f prime of 0 over 1 factorial times x plus f double prime of 0 over 2 factorial times x squared, and then you can continue forever. So this is going to be the case. So f of x can be estimated by the Maclaurin series or the Taylor series, which is going to be nth derivative of f at 0 over n factorial x to the n from 0 to infinity. Okay, so this is going to be the Taylor series as, okay, that's a Taylor series, okay, about 0, about 0, okay, that's it. Or you know that, or this is going to be Maclaurin series. Maclaurin, A-I-N, Maclaurin series. Everything that I wrote, the sine, cosine, exponential function, all of them are Maclaurin series. Okay, I've seen this in calculus. Okay, in calculus 2. Maclaurin is a great guy. Okay, both of them are British. Taylor is an English mathematician, and Maclaurin is Scottish. And some people think that Maclaurin, the only thing he did just replace x by 0 in the Taylor series. Is not the case, really. He has done quite a lot because most of his application is application in engineering and physics. And my PhD advisor was Scottish. So I know everything about Maclaurin. He graduated from University of Glasgow. And I visited that university in 1979 with my advisors. But when we get to this university, at the entrance, you will see the names of the people who graduated from this university. Max Planck, or you see Maclaurin. My advisor told me that, it's a shame for the University of Glasgow to put the name over there, because when he graduated, he applied for a job and they didn't, hire him. But he went down to Edinburgh, at the University of Edinburgh, which is a great university over there. I visited that one too. But in that time, somebody should die so that you will get a job again at that, as a professor at that department. So Newton was very fond of Maclaurin because of his activities, with Newton on those application in mechanics or physics, etc. So he paid for his tuition, he paid for salary, so he can be a kind of, you call it tutor or something, to be at that department, to be around really. But he was around over there, but later on he went to St. Andrews again in Scotland. He got the job, but eventually, he get a job at the University of Edinburgh. So if you visit that university, which is a beautiful one, so the science building is called Colin Maclaurin building, really. So that's one. The other thing is he was a very good teacher. The first calculus book in Scotland is written by Maclaurin, and it's still around. His book is the one that they usually use, over there. They don't change anything, easily. So that's a story about the Maclaurin, really. You can read it for yourself. Has done quite a job, quite a nice job related to the mostly engineering rather than this format. Okay, so that's it. Maclaurin series. So what's going to be your job? You see, when you want to do the power series solution of a differential equation would be given to you, want to solve it. So you assume that the solution, if you call it f of x or y, you assume that y would have a power series, Maclaurin series. You write this Maclaurin series, then you drop it into the equation. You know that the series are differentiable, integrable. So you drop it into the series, and then you just use algebra. Two series are going to be equal to each other, like the polynomials. The two polynomials are equal to each other if the coefficient of the corresponding monomials are going to be the same. So we do the same thing over here. We let the coefficient of the series to be equal to each other, and eventually we find out what is going to be the series solution to your equation. That's all you are going to do. But there is only one thing that you have to do for us. You see, when you have a combination of these sigmas. If you want to identify the coefficient of the given series, if you have two series, you add them together in order to find out what is going to be actually the coefficient. You have a kind of factor those x to the n to be able, to let the equation. So this factoring, sometimes the powers are going to be different. So you have to arrange the series nicely. This example that I'll give you is your job. So make sure you understand this one, but we don't have anything else. It's just playing with this series and be patient to get through it. Okay, so this is going to be the tool or the main example that we need to be able to take care of this problem. There you are. How we're going to combine two series. That's the idea. So we want to do this one in all the problems. Write this, look at this one. I have sigma r 2 times n Cn x to the n minus 1. This is one series, n going from 1 to infinity. Okay, plus the second one, sigma of 6 Cn x to the n plus 1. N plus 1, n equal to the 0 to infinity. You see, this is two series. Would like you to combine them as to one series. Okay, write it as, as what? As one power series. One power series. That's it. You see, if you want to write them as a one power series, what you should have is, you see, if you arrange these sigmas so that they will start together, if you like. You see, this is start from n equal to 1 equal to the 0. Then end up the same thing, if you like. You see, you should be able, if you drop the sigma, then you should be able to factor out the x, because your series is what? Sigma of Cn x to the n. So you check to see if you need to do any changes. Check these two together to see if you can start with the same powers of x. Okay. So if you replace n by 1, what are you going to get here? Focus on the x, on the power of the x. If we replace n by 1, that give you x to the 0. So that give you 1. So the first term of this would be a constant. But if you check here, if you replace n by 0, what are you going to get? N by 0, you get the x. So this would start with the constant. This would start with the x. So if you want to combine them together, both of them should start with the, start with the same terms, if you like. So you have to arrange it yourself. So you go back to see what you can do. You see? So you know that this, the first power of the x that we're going to have over here is going to be x. But here, you're going to have x to the 0 first, then x. So the difference is going to be that constant term of the first one. So what we are going to do is we are going to pull out the constant term here. If we represent by 1, that give a constant term. Then if you pull out the constant term, everything else, you see your next term would be x squared to the third to the fourth, and then would be exactly the same as the other. So you check them together to see this would have, if you like, this would have one more term than the other one, because this is starting with the constant term. So what I'm going to do, I'm going to pull out a constant term here. Okay, so solution. So I'm going to rewrite it. So this is the given one. 2n Cn x to the n minus 1, n from 1 to infinity, plus a sigma of 6 Cn x to the n plus 1, and 0 to infinity. So what I'm going to do is, this is going to be equal to, if we replace n by 1, if we replace n by 1, you see what you get over here is going to be 2c1. It's going to be 2c1 x to the 0, and 1 minus 1 x to the 0. That's the first step. But I keep the other one. So it's going to be plus the same sigma of 2n Cn x to the n minus 1. Okay, I already got the 1, so n would be n equal to 2 to infinity. Okay, so I pull out the constant term here. I pull out the first step. The first step is when you replace n by 1. I pull out the first term plus the rest, n equal to 2. Okay, so look at this one. If you replace n by 2, that gives you 2 minus 1. So your first term would be x. Now look at the next one. So this is going to be plus. What is the second one? The second one, if you replace n by 0, the first term would be x. So you don't need to do anything else with the other one. So you repeat the second one. So that gives you 6 Cn x to the n plus 1, n from 0 to infinity. Any question? So I manage it, or I arrange it so that I have the same powers of the x here. Then I can factor it out. Now you have to take care of these indexes. You see this is x to the n minus 1, this is x to the n plus 1. So what you would like to do, you'd like to have something like x to the k, so that you'll be able to pull it out as a factor. So what I'm going to do, I'm going to change this one. Okay, this is n minus 1. I'm going to take n minus 1 to be equal to the k. So this would be x to the k. Okay? But you have to change everything, okay? So this is going to be, I let k equal to the n minus 1. Then I solve for n. So n would be equal to the k plus 1. Okay? So go back here. Replace n by k plus 1. Then I have to take care of something else. This is start from n equal to 2. I change it to the k. So for n equal to 2, what's going to be k? If n equal to 2, so your k would be what? Would be 2 minus 1, which is equal to 1. Okay? So now I know what would happen. Okay, so I'm going to take this one again. So I bring it here. So this is going to be equal to, you do this right away. So the first one, x to the 0 would be 1. So I get 2c1 plus sigma of, this is n equal to 2. N equal to 2 is equivalent to the k equal to 1. So it's going to be k equal to 1 to infinity. Replace the n by k plus 1. So that gives you 2 times k plus 1. Cn, what is n? K plus 1, x to the k minus 1 equal to the k. So I change this one into the x to the k. Any question? Do the same thing to the other one. What's going to be the other one? We are going to work to get a common factor out. Common factor out, okay? Focus on the power. N minus 1, we call it k. Okay, it's just pushing the power if you like 1 unit. K is n minus 1, okay? So n would be k plus 1. We change everything to this one, okay? Now going to the next one. What are we going to do the next one? In the next one, the power is n plus 1. So this time you are going to pick the k to be, okay, k to be what? K to be n plus 1. if k to be n plus 1, so n would be what? Would be k minus 1. Do the same thing here. But this start with n equal to the 0. When n is equal to the 0, so k would be equal to 1. Okay, so now the second one would be what? Sigma of. When n is equal to the 0, k is 1. So that gives k equal to 1. To infinity. 6Cn. 6Cn. What is n? N is k minus 1. K minus 1. X to the n plus 1. N plus 1 is k. Look at this one. So it's a start k1 to infinity, k1 to infinity, x to the k, x to the k. You can combine them together. Yes.
How come you're able to call k n minus 1 and also n plus 1?
It doesn't matter. K is a number. Is the index. You call it t. It doesn't matter.
Okay.
It's important that it's a start from 1 to infinity.
Okay.
You see, that's one. So you have a number which is 1 to infinity. Call it t, call it k. Because if you expand it, remember, if you expand it, expansion would be in both cases what? X squared, x to the 4, to the 5th, to the 6th. The second one, the same thing. It doesn't matter whether you call it k and you call it. Okay, that's fine. Yes.
So for your n equals 0, and then it
Yeah.
goes to k equals 1, wouldn't it be 0 minus 1? So wouldn't the k be minus 1?
For what?
Like,
Now, you see, n start from 0 here, okay?
yeah,
And it start from 0, what I said, 0 would be equivalent to the k equal to 1 here. Okay, so it's going to be k equal to 1 to infinity. But if you want to do the n, okay, n equal to 1,
oh yeah,
n equal to 1, k would be 2 this time. Okay, to get these numbers. Yes.
And the reason why we changed it from n equals 1 to n equals 2, so that when we solve for k, our n would be, or our k is equal to 1, so it goes from 1 to infinity. right?
Yeah, that's fine. You see, if you list it as an expanded form, you will see nothing would change in this case. But since you want to write it down in condensed form, so this must be consistent. That's it. That's because you see, what I want to do now is I just want to put them together. So if you want to put them together, it's like sigma would be the sigma, and it's like factoring x to the k out. So that's why you have to, because this is like a polynomial. If you want to combine the two polynomials, what you do? You combine the like terms. So this is the way we introduce those like terms to get these numbers. Because those k in the names are not important. The important part is that you see the powers, the order of the powers should be to see k equal to 1. So you start your powers of the polynomial or the series would be what? X squared to the 3rd, to the 4th, to the 6th. Over here, this again the same thing. X squared to the 4th, to the 6th. So you can factor out all those, combining all those like terms. And this is how you condense it in a minute.
I guess what I was just kind of confused about is how 1k is n minus 1, and then like the same k is n plus 1.
Doesn't matter. You don't like the k?
No,
Change it
I'm
for you.
fine that it's k. It's just we're saying that two things. One's n plus 1 and the other one is n.
Don't forget about the k. You just read the term of this series.
Okay.
What is the first power of the x? Of the x here. Then you replace whatever it is.
1
You call this one t. So the first term would be what?
x to
Would
t.
be x. With x to the t. If t is 1, the first power would be what? X. The second one, x squared to the 4 to the 6. Okay. But if I call it k, it's the same thing. You see, the first power would be x squared to the 3rd, to the 4 to the 6. Okay, they're all going to be the same thing. That's why we call them the same thing. Okay, because it's the powers are going to be the same. You know, just the name. Because you see, your target is to combine them together. You combine them together, you factor out these terms. Like two polynomials you have. You see, if you have 5x squared and 7x squared, 5 and 7 would be 12x squared. This is why we are arranged in this format now, to be able to do it, combine it together. Okay, any question? Because since you eventually you make it into one series, so you better use the same index, to put them together. Okay, are you happy? Next, this is now it's ready. So this is going to be equal to what? Safely we can say, okay, through C1, you can't do anything about this one. You have to keep it as is. Now you can put everything else together. So look at this. Because the indexes are the same, you see, and the powers are the same. So that would be 2 times. Okay, so it's a 2 times class k plus 1. It's a kind of, I'm going to factor these out, see? So I have 2k plus 1, ck plus 1 as a coefficient of this x to the k, and for the other one would be plus 6c to the k minus 1. Now look at this as a factor, all x to the k. So that's why you have to use the same k to be able to write it down here together. Now this is going to be a new power series, okay? A new power series, and it's only a single power series. If you use the t and the k, then you'll be in trouble over here. You cannot do it. If you have, if you have x to the k here and x to the whatever. Okay, any question? If you don't feel happy about it, just write down the terms. Write down the terms, just a couple of terms of the first one, couple of terms of the other one. You will see that it's going to be the same procedure. Yes.
Would you run into problems if you had like a coefficient on the end on the original one, like if there's 2n plus 1, and then like an n minus 1, you could not combine this, right?
No, it would be messy, but no. Because if you get that 2n plus 1, probably you may have that 2n plus 1 on the top. See, then you call that one kk. Okay, we are going to have the cosine case. No, it's running nicely. Right. The only difficulty is this part, you see, to manage that the starting point is going to be the same thing. Sometimes you may have to pull out a couple of terms. Depends on that n minus 1 that you have. If one of them is going to be n minus 3, then you may pull out a couple of more terms to make it balance. You see, you have to make a balance to be able to factor out that term out. And don't worry, in any problem, this is the one you are going to do. Okay, to get this through. Okay, any question? Good the idea, everybody. Let's do it. We give a differential equation, and we're going to solve it by this power series. Okay, so of course, it's not going to be a complicated one because you can't do it. Okay, at most the power of the 2 would be enough to get this through. Okay, so these are going to be the one. And we give you something short because it takes time. So the first one is this one. We want to find a solution. Okay, find a solution of this equation or the solution. So find the solution of this equation, y prime minus 2xy equal to the 0. Okay, in the form of, this is the expression of your book, in the form of power series, the power series in X for the Maclaurin series. That's it. So this is the way we're going to do it. You suppose the solution is just a power series, okay? So your y is going to be your function. So you suppose y equal to sigma of Cn x to the n from 0 to infinity is the solution. Is a solution, okay, a solution of the equation. So you assume that the power series is your solution. Now, if it's gonna be a solution, it satisfies the equation, so you have to substitute it here. Since you need the y prime, differentiate it first, okay, then substitute. So you note that y prime, you know that if you want to differentiate the power series, you just differentiate x to the n. So this is going to be sigma r n Cn x to the n minus 1. And you know that you got to be careful and start from 1 to infinity. You cannot have a negative power for power series. Okay? Now go back and substitute into the equation. In the equation. So the equation is y prime minus 2xy equal to 0. It must satisfy this equation. Okay, substitute. So this is it. It's going to be sigma of n Cn x to the n minus 1, n from 1 to infinity, minus 2x times sigma of Cn x to the n from 0 to infinity. And this is going to be equal to what? Is going to be equal to the 0. This is the case. Now you have to take the, you multiply the 2x inside, okay? Because you have to get the powers of x. So we continue, that give you sigma of n Cn x to the n minus 1. The first one, n from 1 to infinity. And this is going to be minus sigma of, just explain it, you know, just take the 2x inside, 2x times Cn, that's x. 2x Cn x to the n from 0 to infinity, okay, equal to the 0. X times x to the n would be x to the n plus 1. So that gives a sigma of n Cn x to the n minus 1, n from 1 to infinity. It's going to be minus sigma of 2Cn x to the n plus 1, okay, n from 0 to infinity. N from 0 to infinity, and this is going to be equal to the, okay, equal to the 0. This is your substitution. Now you have to combine them together. You check to see if the first terms are going to be the same, if you like. Do you need to pull out anything from these? Okay, you check it. If you replace n by 1 over here, replace n by 1, you get a constant here, because that's 1 minus 1. Okay, and over here, if you replace n by 0, replace by n by 0, you get the x. So this is start from a constant term, and this is start from the x. So in order to balance it again, you have to pull out this constant term out, so that your first term would be x. Okay, this is the way we do it. Any question? You check the first term, you see when n equal to the 1, the first term x to the 0 would be 1. You get a constant. But if you replace n by 0, that give you x. So you cannot factor out the x's if you like. So what you do is, you are going to pull out the constant term so that this is start from the x and this is start from the x. Okay? Pull out the constant term, replace n by 1. N by 1, that give you what? That give you C1. I write it down, it's going to be 1 C1 x to the, okay, x to the 0. That's the first term of this series. Now bring it again, it's sigma of n Cn x to the n minus 1. Now this time n start from 2 to infinity. 2 to infinity because you already got the 1 out. Any question? You see, look at this one now. When n is equal to 2, that gives you x. So the first term of this involves the x. Now look, check the second one. If we check it, the second one is fine. Nothing to worry about because it starts from the x. So repeat the second one as is. 2Cn x to the n plus 1, n from 0 to infinity. Okay, equal to the 0. Now we manage the first term. Now you have to manage the indexes. Okay, so what you do is, so this x to the 0 would be 1. So that give you C1 plus sigma r change. So we're going to change this one. This is n minus one. We're going to call n minus one k. You can do it outside, just come back and do it for us. We accept it. Okay, so this is how I manage this one. So I take a k to be equal to the n minus one. So n would be k plus one. Okay, k plus one. And when n is equal to 2, k would be equal to 1. Okay, I take the power to be k. I solve for n would be k plus 1. You start from 2, so when n is equal to 2, k would be 1. So now the sigma in terms of the k would be what? K from 1 to infinity. K from 1 to infinity, n is k plus 1. K plus 1. Cn, c, k plus 1, x to the n plus n minus 1, which is equal to the k. Okay, nothing has changed, you see. When you replace k by 1, you get the x here. Now we do the same thing to the other one. So it's going to be plus. You see, the other one is going to be what? The same thing. And now for the second one, I replace the k by n plus 1. So I replace the k by n plus 1 for the second one. Then I find n, which is going to be k minus 1. When n is equal to the 0, n equal to the 0, k would be equal to 1 for the second one. Okay, so the second one would be sigma of sigma what? K from 1 to infinity. 1 to infinity, 2Cn. What is the n this time? Is k minus 1, x to the k, equal to the 0. See, we arrange it so that the beginning of the series are the same, and all the powers are the same. Now we can combine them together to get these indexes. Any question? Yes.
Why did we change the minus to a plus sign on the third?
Minus, where's the minus 20?
Like 2 lines up,
Three in the series.
You see,
Higher,
a little bit more up.
this one,
between 2 series on like the third line.
1, 2, 3.
No.
You see, because n start from 2 here, replace 2, 2 minus 1 would be 1.
A little higher. You have this the 2 series are subtracting
Oh,
each other,
yeah.
and then you turn it.
Oh. The minus, okay, thank you. That was a mistake. Minus, thank you. I thought, minus is. Very good, okay, any question? Combine them together now. So what's going to be the case? It's a C1. Change it to the 1 series, K1 to infinity. You factor out x to the k and you identify the leftover. So what's going to be the leftover? It's going to be k plus 1. The ck plus 1. That's coefficient of the first one. And it's going to be plus 2 ck minus 1. That's coefficient of the second one. All of them times what? Times x to the k equal to the 0.
It's still gonna be minus 2c.
Minus. We will just write positive. Okay, minus. Any question? Now we have one series to the left, one series to the right. Series to the right is 0 series. Okay, so all the coefficient of this new one is, see, you can write this one if you like as, you see, you can write this one as what? As 0 plus sigma of 0 x to the k and k from 1 to infinity. Because two series are going to be the same if their coefficients are the same. So the coefficients are going to be what? So this means C1 is equal to the 0. Okay, so we get a C1 is equal to the 0. And the coefficient of the series over here is what? Is a k plus 1. Ck plus 1 minus 2 ck minus 1. Okay, this is going to be equal to the 0. And the relationship between the coefficients. We have done the discrete mathematics. you should be familiar with this type of things that we do. We call it recursive relations for this part. Okay, and so you have to work on this one because this is going to be a relationship between those terms. Solve it for the higher index. So the higher index is CK plus 1. Okay, so move the other one to the other side. So this is going to be K plus 1. Okay, K plus 1, this is CK plus 1. Okay, it's equal to the 2 times CK minus 1. Okay, solve for CK plus 1. So that give you CK plus 1 equal to, divide both sides by K plus 1. So that give you 2 over what? 2 over K plus 1, 2 over K plus 1, CK minus 1, CK minus 1. Now you know that the K would start with over here. You already got the C1, which is equal to the 0. So K start from 1, 2, 3. K is 1, 2, 3, etc. So you got this equation that we call it recurrence relation. So this means you move around this. Okay, replace K by 1, 2, 3, 4, 5, 6. Anytime if you replace K by 1, so you end up C zeros here. You already got the C, you got the C1 here, okay? That was C1, yeah. We got the C1, okay, and then we try a couple of times. If it's going to be I'm going to go this one to give you right through the end. But if it's going to be something that's going to be unfamiliar, we usually always go for the 5 terms to identify, to get an idea of what's going to be the solution of the equation. But it's not bad. So, any questions so far? I'm going to go to the next page. I'm going to try this. Okay, replace K 1, 2, 3, 4, 5, 6 to see what's going on. See, after 5, you may see what is the nature of the series. Yes.
Why do you start K at 1, not 0?
You cannot have a 0 because this is K minus 1.
Oh, so it's okay.
Because C negative 1 does not exist.
The first term would have to be like C of 0.
Yeah, because those, yeah. Because that those bottom can be 0, 1, 2, 3, 4, 5, 6. That's why I check it first to get enough to write it down. Okay, so let's go to the next page and try this. Okay, try it for some number of K to see what is the nature of this equation. Okay, so I'm going to write it for myself again. So I have a CK plus 1, which is equal to the 2 over the K plus 1, okay, and CK minus 1. And this is true for K equal to the 1, 2, 3, etc. And I already got another one. I got the C1, which is equal to the 0. Remember, this is the C1. So let's try some numbers. So we start with the K equal to 1 in this equation. So if you put K equal to 1, you see here 1 and 1 would be 2. So that gives you C2 equal to the 2 over. I write it down so you know what's going on. 1 plus 1. And you get the C0. C0. Okay, C0, so that gives you 2 over 2. C0, which is going to be equal to the C0. So C2 would be C0. You don't have the C0, doesn't matter. This is differential equation of the first order. So you can have one constant, remember? So you may think about this constant to be your C0. Okay, so this is it. Continue. K equal to 2. Go to the equation, substitutes K equal to 2. 2 plus 1 would be 3, so we get C3 equal to the 2 over 2 plus 1. 2 plus 1, C of C1. So that gives you 2/3 of the C1. But remember, C1 is 0. C1 is 0, so that gives you 2/3 times 0, which is equal to this. So C3 would be 0. So there is no X cubed solution. Okay, any question? So let's try another one. K equal to 3. If you put K equal to 3 here, so that give you C4. C4 is equal to the 2 over 3 plus 1. 3 plus 1, and that's going to be 3 minus 1, which is going to be C2. So that give you 2 over 4 C2. Okay, it's going to be 1/2 of a C2. But remember the C2, okay? And remember the C2 is C0. Okay, so C2 is equal to the C0. So that would implies that the C4 is going to be 1/2 of the C0. Okay, so that would be C4. Let's try one more. The idea, then we can write it down. We usually go with the 5. Then we check to see if it's going to be something nice. So K equal to 4. Go back, that give you C5 is equal to the 2 over 4 plus 2. C3. Okay, C3, that give you 2, 6. Okay, that give you 2, 6, C3. At C3 is 0. So that give you 2, 6 times 0. Times 0, so the result would be 0. C5 would be 0. So that will show you that those odd indexes are going to be all 0. Okay, to get these numbers, I get the 5, and then I list that. C5. You go with the 5, okay, fifth line. So that gives C6 now. C6 equal to the 2 over 5 plus 1 C4. So that gives you 2, 6. Okay, that was true. That's going to be. So I go with the 5. That's going to be C6, C4. That was, what is the C4? Yeah, we have the C4. So it's going to be C4, which is going to be 1/3 of the C4. But C4 was, C4 is 1/2 of the C0. So that gives you the fact that the C6 is going to be equal to the 1/3 times 1/2 of the C0. It's going to be like a 1/6 of the C0. And the 6 is 1 over 3 factorial C0. Give an idea of what is going to be on for this problem. Okay, that's going to be C6. So C6 is going to be 1 over 3 factorial C0. Okay, and then you can continue. As you can see, if you get the odd indexes, they are all zeros. So if you continue, you would find out that the C for the odd, 2n plus 1, 2n plus 1 is equal to the 0. And in case of the even one, if you get a C2n, you see the even? This is 6, 2 times 3, 3 factorial. The C4. C4 was what? What is the C4? C4 is 1/2 of the C0, which is going to be 2 factorial. So this means C2n is going to be 1 over n factorial. Okay, this is going to be 1 over n factorial C0. Of course, this is easy and nice. We get all this together. Now we can combine them together. If it's going to be something like, like this one that you see, you do it. And if the coefficient are going to be kind of complicated one, we just write it down as those 5 terms. They give you the hint. If they ask you 5, just the first 5 terms, this means it's not going to be something nice that you'll be able to list it for us, okay? And this is nice. Put them together to see if you can get it. Any question? So we guess what is going to be the solution. Now, let's see if we can identify the solution. So what's the solution? Remember y equal to the sigma of Cn x to the n from 0 to infinity. That's the case. In general, this is going to be C0, C1x, C2x squared, C3 x cubed, etc. Now substitute the one that you have. The one that we have C0, C1 is 0 because odd index are 0. C1 is 0, but the C2, okay, that's going to be C1 is 0. C2 was C0. Okay, C2 was yes, we got the C2 was that's it, yes, C2 was C0. So it's going to be C0 x squared. C3 was 0. C4, okay, what's a C4? C4 was 1 over 2 factorial. 1 over 2 factorial C0 x squared. Okay, this is going to be 0, and then you continue. So this is it. The y is going to be equal to, we got the C0 x squared plus 1 over 2 factorial C0 x to the 4th. Okay, plus, you see that's 4, the other one would be 6. It's going to be 1 over 3 factorial C0 x to the 6. Okay, etc. So that's a 6, 2 times 6. That give you the factorial over here. Okay, so that's a 4, 6. And so you can pull out the C0 to see if you can find out what function is this one. 1 plus x squared plus x to the 4th over 2 factorial plus x to the 6 over 3 factorial plus x to the 8 over 4 factorial, etc. Can you guess which of those series that I gave you is this one as a function? Is it exponential, is it sine, or is it cosine?
Sine.
No,
Is it, it's exponential.
it must be exponential, but exponent of what? You see, if you call x squared to be equal to t, for example, this would be 1 plus t over t squared over 2 factorial, t cubed over 3 factorial, etc. It would be e to the t. But if you take the t, it will be x squared. So it's e to the x squared. See, this is going to be equal to the C0 e to the x squared. The solution of the equation. Of course, you know, they are not going to be the case for all of them to be able to find out. Remember, that's the case that you see e to the t is the sigma of t to the n over n factorial. So e to the x squared sigma of x to the 2n over 2n. Okay, and if you solve the equation, of course, it was very easy to solve the equation originally. Solve it, you can check it to see the, okay, note that. What was the original equation? You see, you have a y prime equal to the 2xy. If you change the y prime into the dy dx, separable. If you multiply, cross multiply, so that give you dy over y equal to the 2x dx. Now, if you integrate it, integral of dy over y, integral of a 2x dx, that give you ln of y, or the absolute value of y. And this is going to be x squared plus c. And if you write down an exponential form, y would be e to the x squared plus c, which is e to the x squared times c, or the c naught. Sorry, times e to the c, you can call this one c naught. So c naught e to the x squared is going to be the final answer. So that's going to be the idea of doing it. As you can see, it's, you know, you got to be patient. It is the easiest one to be able to, it takes time, but it would be lots of fun. I give a break and then we try another one, which is gonna be a little more involved, okay? But again, we would like to get the idea in case you need it, but there are some software that give you the solution of these type of equations. There are some, if you, depends on what you're going to do in future, there are some equation that the only solution is going to be power series solution, but you estimate only. Not the exact solution. Okay, coming back and give you something, a second order, if you like. Even just put your email,
Yes.
just attach it to that comment part.
I thought I did.
I haven't checked it. I saw that you send it to me, yeah?
Yeah.
Attach it to the comment section of
Oh,
that.
the comments section.
Yeah, that would be easier because I'm not going to lose it.
Okay, I'll do that.
Okay, let's give you another example. It's kind of, this was, the first one was the first order differential equation, except one with the second order. Okay, so. This is going to be the second one. Let's solve this equation. To find the solution. This equation for y double prime plus y equal to 0, of course, in the form of, okay, in the form of the power series. Show you how you handle when it's when this is second order. Okay, again, you start with the, you suggest the solution to be a power series, a Maclaurin series. And you substitute it, okay, already solution. Suppose your solution is this. It's y equal to the sigma of Cn, h to the n from 0 to infinity is going to be a solution. Okay, it's going to be a solution. Then you want to substitute here, you need to go with the y double prime. So differentiate it twice. Then if you differentiate it once, that give you y prime, which is a sigma of n Cn x to the n minus 1. Okay, and from 1 to infinity. Then you need y double prime. So differentiate it again. So that give y double prime, sigma of, you know, you just differentiate x to the n minus 1. It's going to n minus 1, x to the n minus 2. So it's going to be n times n minus 1 times Cn x to the n minus 2. And this time n goes from 2 to infinity. Anytime you arrange the index of the sigma, you must make sure that you're not going to be reducing a negative power for the x. Okay, now go to the equation, substitute. Okay, so the equation is 4y double prime plus y equal to 0. Now substitute. It's going to be 4 times the first one. I just multiplied the 4 inside. So it's going to be 4n times n minus 1. Okay, Cn x to the n minus 2. N goes from 2 to infinity. Okay, that's the 4y double prime plus y. So it's going to be plus sigma of Cn x to the n from 0 to infinity. This must be 0. That's it. So check to see what's going to be the first term. Are you going to pull out anything? Just replacing those. So if you replace n by 2, that gives you x to the 0. So the first term over here is going to be a constant term. And over here, if you replace n by 0, that gives you the first term would be just the constant. So you don't need to do anything extra. So change the index. Okay, to change the index, I go with the first one. In the case of the first one, I need to change the k into the n minus 2. Okay, so n would be k plus 2. And over here, n start from the 2. So when n is equal to 2, k would be 2 minus 2, which is 0. Okay, so we're going to change the first one. Any question? So you top one, you see the top of it, you make it into the k. You have to change the starting point. So the result is going to be sigma of, and now k start from 0 here. So k equal to the 0 to infinity. Change the n. That gives 4n. It's going to be 4 times k plus 2. K times n minus 1. Okay, n minus 1. This is k plus 2. N minus 1 will be 1 down, so that gives you k plus 1. Okay, that gives you k plus 1. You have cn, ck plus 2. Now x to the k. So that's how we change the first one. Any question? Second one is easy because nothing would change. But we change the n to the k so that we have the same index. So this is going to be plus sigma r, that give you k from 0 to infinity. This is going to be ck x to the k, and this 0. Okay. Now combine them together. So it's going to be sigma of the combination. It's going to be 4 times k plus 2 times k plus 1, ck plus 2. That's the first coefficient of the first one. The coefficient of the second one is the ck. So it's going to be plus ck. You factor out x to the k equal to the 0. That k goes from 0 to infinity. That's it. There is nothing extra, so you just let the coefficient to be equal to the 0, and then make that the recurrence relation coefficients. You let this coefficient to be equal to the 0. So that gives you 4 times k plus 2, k plus 1, ck plus 2, plus ck equal to the 0. Okay, so for the higher index, higher index is ck plus 2. So move the ck to the other side and divide by this coefficient. Okay, so it's going to be 4 times k plus 2 times k plus 1, ck plus 2 equal to the negative ck. Divide by the coefficient. So that gives you ck plus 2 equal to, it's going to be negative 1 over 4 times k plus 2 times k plus 1, k ck, ck. And the k can start from 0, 1, 2, 3, etc. Just check, you see if you put this k equal to the 0, that gives C0. So there's nothing wrong. So this is going to be recurrence relation that will give you all the coefficients. You start writing a couple of them, 4 or 5 terms to see what's going on. If it's going to be familiar, we can change it to the familiar function. Otherwise, We just list it. Remember, this is the equation, differential equation of a second order. So you can have two constants, okay? Two constants, because it's a wide difference. We'll put the next page and start working for this one. Okay, question, are you done? So let's pick some numbers in that relation that we have. I write it down for myself again, ck plus 2 negative 2 times k plus 2 plus 1 ck. Here is the one that we have. So start with the k equal to the 0. Put the k equal to the 0, give you c2 equal to. Okay, now down the bottom it's going to be negative. If you replace k by 0, that gives you 4 times 2 times 1. Okay, 4 times 2 times 1, which means going to be, okay, it's going to be c8. Sorry, times it by c0. C0, this is going to be negative 1/8. Negative 1/8 c0. So that would be your c2. So c2 is going to be negative 1/8 c0. Remember, you can have two constants. So it doesn't matter to have the c0 at the moment. Okay, there you are. Any question? Continue. K equal to 1. K equal to 1, 1 and 2 would be 3. So that gives C3. Okay, so that gives you C3 equal to negative. If you put K equal to 1, so you get a 4 here. 4 times K equal to 1, that gives you 3. K equal to 1, that gives you 2. And the, okay, and the C1. Okay, 4 times 3, 12, 24. So that gives you negative 1 over 24, C1. Again, it's okay. We can have two constants and you don't have the C1. So you are going to get this, sorry, that is a C, yeah. So that gives us a C3. So C3 would be negative 1 over 24, C1. Again, you can have two constants. So it's okay to have the C0 and the C1 so far. We'll try it again. K equal to 2, any question? Just getting a couple of more terms to see if we can have a good idea of what's going on. So replace K by 2. If we replace K by 2, 2 and 2 would be 4. So that gives you C4 equal to 1 over 4. Replace K by 2. 2 and 2 would be 4. Okay, 2 and 1 would be 3. C2. What is the negative sign here? Okay, that give you, this is it. That gives you 16 and 16, 48. So that give you negative 1 over 48, C2. And you already got the C2. C2 is a negative 1 over 8. Okay. So C2 is going to be, so this is going to be negative 1 over 48. Okay, substitute for the C2. So the C2 is negative 1 over 8 C naught. Okay, C naught, if you put it together, so that gives you C4. So that gives you C4, which is going to be equal to the, okay, negative will be positive, and that gives you 48 times 8. I'm going to take care of this in a minute. C0. So that's a situation that you're going to have if you just continue getting these numbers. So, you know, you can, if you want to find a relationship between these coefficients, you can start with the fact that, for example, 8 is, you don't have to, but I just want to give you, because this is nice. but it's not going to be the case all the time. So what we did so far is you have your C2, which is -1 over 8 C naught. C2, you can write down as a 1 over, you can write this one as a 4 times 2. So it's going to be 4 times 2. 4 is, this is it, 4 times 2 C naught. It says 2 squared. You may think about this one 2 factorial, because it's going to be a nice version. You'll see it in a minute. So that would be your C2. Let's see if we can make C3 as something like this one. So that was a 2 and the 2. So a C3 is a -1 over 24 C1. So if you want to make something similar to this one, what is going to be 24? 24 is 3 times 8. So it's going to be equal to the 8 times 3 of the C1. Okay, and if you want to make something nice, so 3 times 8 would be the case. Didn't miss anything over here. It was 20. Okay, so you can write this one as 2 cubed. So it's going to be -1 over 2 cubed times 3. Just checking again for the C3. We did have C1 over 24. Okay, if you want to make it a factorial, so this is going to be 2 squared times 3 factor. 3 factor would be 6. You see, this is going to be something like 4 times 6. 4 times 6, you get C, okay, factorial times it by C1. That would give you some idea of what is going to be the next term. You see C4. C4 is equal to what? So in a case of the, let's make sure we substitute this one. Yeah. In the case of the C4, you see the C4 is, if you want to make something similar, was 48 times 8 C naught. So this is going to be something like, if you want to make it like this, so you should have 4 times 4 factorial. Because 3 factorial would be 6. 4 factorial would be 4 times 6, which is 24. Okay, so that gives you an idea of how these terms are going to be arranged. Now, if you put them together, even if you don't want to do this one, you have to do this to tell us what is the sort of solution you have. So let's see. Y was what? Sigma of Cn x to the n. This is C0 plus C1x, C2x squared, etc. Yes,
4 factorial is
4
24.
factorial is 24.
And,
And 24, and that was 24 times 4.
oh, 24 times 8, yeah,
Yeah,
okay,
we just arrange it. We get the hint from the previous part.
okay.
Okay?
Yeah.
So let's put them together to see if we can make something nice. You see, if you substitute, what's going to be the result? It's going to be equal to C0 is a C0. A C1, you don't have anything for the C1. It's going to be C1x. But for the C2, you did have this one for the C2. So it's going to be 1 over 2 squared, 2 factorial, C naught x squared. You see that's going to be for C2. For a C3, you get the -1 over 2 squared, 3 factorial, okay, and C1, that give you x cubed. And for the next one, you have 1 over 2 squared, 4 factorial, C naught x to the 4th, etc. Now you have to group them into 2 parts because Remember, your equation is of the second order. Remember, general solution of the second order equation is what? C1y1 plus C2y2. So you have to have this type of arrangement, even if you don't want to write full solutions. And this is it. Look at this. You have some with the C notes. So I'm going to group them into two parts. I factor out the one with the C note. I put them together. See, I have the C naught minus 1/2 squared times 2 factorial C naught. Then the next one is going to be 1 plus 2 squared times 4 factorial. These are going to be there. Okay, that's a C naught. This is x squared. This is x to the 4th. And you continue to get this even power. Then it's going to be plus the odd power coming with those coefficients that we have here. You see, for the odd powers, you start with the C1x. You see C1x. Then you have negative 1/2 squared, 3 factorial x cubed. And even you can have to write the next one. This one is going to be, of course, it's a C1 again. So the next one is going to be C1, 2 squared, 5 factorial, x to the 5th, and you continue. Okay. And there is a C note here too. It's a C note, C note, C note for all of them. C1, C1, C1 for the others. Now you factor out the C note from the first part. If you factor out the C note, the leftover is going to be 1 minus 1/2 factorial, 2 squared, 2 factorial, x squared, plus 1/2 squared, 4 factorial, x to the 4th. That's the first one. If you pull out the C1 from the second part, that gives x minus 1/2 squared, 3 factorial, x cubed, and those continue. So you may call the first one, you may call this function as y1, this function as y2. So your solution is going to be cy1 plus cy2. The general solution of the equation. Okay, so it's going to be this type of format, or this type of equation. As you can see, it's not difficult. It takes time to be able, to take care of it. It's the type of a problem. Can you guess what is y1 and y2?
Cosine,
This one?
sine, cosine.
Yes, sine and cosine. See if you check this one. This is even power. Even power that we have. Of course, it's not going to be cosine x, because the cosine is what? Is 1 minus x squared over 2 factorial. That's x to the 4th over 4 factorial, etc. So it's going to be, look at this. You have, this is x squared over 2 factorial. This is one extra term, 1/2 squared, which is 1/4. That would be, okay, that would be repeated again. And so it's going to be kind of x half, because you have the x squared over 2 squared, which is going to be x half squared. So officially, if you like, this is going to be C1 cosine of x half plus C2 sine of x half. When I post this, the notes for you, you will see more solutions of this. Just go for a couple of them. And it's not the case that always, you will get this type of nice format. It's not. So when you get to the test, if you ask for if you go with the 5 terms, we are going to be satisfied. 5 terms of the series. Yes.
So is that an acceptable answer? Just
Yes.
labeling that y1 and then the
That's
other
it,
one
yeah,
y2 and then
yeah.
y is equal to.
Yeah, if it's going to be second order, you have to go to the to the step that you show us that you are going to have a combination of a C1, Y1 and the C2, Y2. Yeah. Yeah, but you cannot leave it like, like the first part.
Okay.
When it's going to be first order, you know that you must have one constant times a function. But since this is second order, you have to group them and show us that, yes, eventually you will arrive at a combination of two functions. That is going to be the case. Okay, so let's see if I can give you one more. You see, the other method, which is not going to be, you cannot use it all the time. But there are some equations that you can use directly, the Taylor methods or the Taylor series to do it, just for your information. This is a very unique, not the case that you'll be able to use it, okay, but it's not bad. Just quickly give you an idea of this format too, and then we finish it. I'm not going to do anything else on this one, okay? So then there's when you get your next practice quiz, problem that we call it Hermite equations. You usually use the power series because you use it in physics or application problems. So I put it into the practice one because it takes time to read it. Let me do at least one of them for you and get to the practice one. Okay, let's see, get this method as well. This cannot be used all the time, but not bad to be aware of this. We want to solve this equation. Y prime plus y equal to 1 by power 6. You can see it's very easy equation to solve. It's a linear equation. But let's say if you want to use the power, use the Taylor series to do it. You see, in this case, the reason that we do it is this one. You see, you can solve this one for y prime. And give y prime equal to the 1 minus y. Then you can differentiate it. You get y double prime. It's very easy. Then you can differentiate it. You see the Taylor series? You see this one? Suppose y equal to the Maclaurin series, you see? And derivative of that at 0, n factorial, x to the n from 0 to infinity, which is equal to the, or y equal to the first term is f of 0. The second one, f prime of 0 times x, f double prime of 0 times x squared over 2 factorial, etc., is the solution or a solution of the equation. Now go and find this, okay? Find this f of 0, etc. that we have. So what we do, the equation is y prime plus y equal to 1. Okay, solve for y prime. So that give you y prime. Okay, y prime equal to the 1 minus y. Evaluate it at 0. So that give you y prime of 0 is equal to the 1 minus y of 0. Okay, y of 0, you can call it C naught because you can have one constant. Okay, so let y of 0, let y of 0 to be equal to the C naught. Then y prime of 0 is equal to the what? 1 minus C naught. This is your f prime of 0. I'm going to find this coefficient for you. So what you have so far is f of 0 is equal to the, okay, so what you have so far, f of 0 is equal to the C naught, and f prime of 0 is equal to the 1 minus C naught. So you have to find f double prime of 0. So I'm going to find f double prime of 0, bring this one and differentiate it. See, y prime is equal to the 1 minus y. Differentiate it. Y double prime is 0 minus y prime. Evaluate it at 0 again. So y double prime of 0 So this is going to be y prime. So y double prime of 0 would be equal to the y prime of 0. At y prime of 0 is 1 minus c naught. Okay, which is equal to the 1 minus c naught. So y double prime of 0 again would be what? Would be 1 minus c naught. So this means f double prime of 0 is 1 minus c naught. Okay, if you continue, all of them are going to be the same thing. Because you can differentiate it again, okay? So you have y double prime equal to the y prime. You differentiate it again, so the y tiers would be y double prime. So y tiers of the 0 would be y double prime of 0, which is 1 minus c naught again. So the same thing. So the third derivative, 0, 1 minus c naught again. So all of them are going to be 1 minus c naught. Okay? So what's going to be your solution? Y equal to f of 0. Remember this, I repeat it again. F of 0. F prime of 0 x. F double prime of 0 x squared over 2 factorial. Now substitute. Would be y equal to that. All of them are 1 minus c naught. So that give you, the first one is of course c naught. So this is 1 minus c naught times x. And the next one would be 1 minus c naught squared. Okay, times x squared over 2 factorial. Okay, etc. Okay. So if you put them together nicely, this is your solution, but you can find out what type of solution do you have. You can factor out that 1 minus c naught, that give an idea. Any question? I can go to the next page. I'm going to factor out, I leave c naught as is. All of them are 1 minus c naught, 1 minus c naught, 1 minus c naught. I factor out 1 minus c naught, and then you will see the function that you are going to have, okay? So this is it. So this is going to be equal to the y equal to the c naught plus 1 minus c naught out. If you factor it out from the rest, so we get what? We get x minus x squared over 2 factorial plus x cubed over 3 factorial, etc. What is this? Which one? Not exactly. Something is missing. You make it e to the x. What is that? No. E to the x is 1 plus x. Remember, e to the x is 1 plus x squared over 2 factorial, etc. 1 is missing. So this is going to be e to the, of course, it's going to be e to the negative x because this is positive, negative, positive, negative. It's going to be e to the negative x minus 1. Because you need a 1. You start with the 1 plus x factorial, etc. Okay, so y would be c naught plus 1 minus c naught times e to the negative x minus 1. Of course, you can multiply it and simplify it. That c naught will disappear. Okay, so that's going to c naught. If you multiply it across, it's going to be 1 minus c naught times e to the negative x plus 1 minus c naught. I multiply 1 minus c naught times the first one and times the second one. So these two would be cancelled out. So the final answer is 1 minus c naught e to the negative x plus 1. Of course, this is a unique equation. If this is good, if this is another option, if the given equation is going to be nice one, which is not going to be the case. Most of the time, it's going to be in terms of the power series. Okay, so that give you an idea of deal with this type of problems. I'm not going to do anything else with problem.